So we're live. Might just give it a few more moments and see if some more people join. Well, we might just get started. So today's webinar is on soil carbon in the Mallee. My name's Jack Caroney. I'm a project officer at Mallee CMA. And today's session is being delivered as part of the Victorian Carbon Farming Outreach Program, which is being delivered in partnership with Landcare Victoria, Agriculture Victoria, and the 10 Victorian CMAs. So today's a fairly short session. I'll go through and introduce Cassandra Schefe shortly, who will talk a bit about the importance of soil carbon in our region and how it links to our farming practices, as well as emissions and productivity. So I just wanted to start by acknowledging the traditional owners of the land that we're all meeting on today, and pay our respect to them, their culture and their elders, past, present and emerging. Just some housekeeping. So this session is being recorded and will be available for viewing on the Mallee CMA YouTube page. Attendees' microphones and cameras are turned off, but everyone is welcome to use the Q&A function to ask any questions that they might have, and we'll have some time at the end of the session to go through any of those questions. I'll also share a link to a feedback survey if anyone would like to provide any feedback on the session, or if they'd like any more information. So today we have Dr Cassandra Schefe, who is a soil scientist and co-owner of AgriSci. Cassie has a vast experience working in agriculture, both in scientific research as well as working on farm, helping growers to understand their soils and the constraints that they face. And if anyone would like to meet Cassie in person, we're I want to mention we're running a workshop next week at Lorraine. So there's a registration link on the screen. We can scan that QR code and sign up for that one. We're encouraging people to bring along some soil test results from their farm. They can have a look at the interpretation of those results. So we'll have a bit more time in that session, runs for 3 hours, so we'll be able to go into some of these topics in a bit more detail. But given today's a fairly short session, I might hand over to Cassie and she can take us through what we've got for today. Just presenting. Here we go, Cassie.
Alrighty, thank you, Jack. So thanks to Jack and the Mallee CMA for inviting me to hang out with you guys this evening. It's always a bit of a challenge to find time to do everything we want to do in our day. So thanks for taking the listen, and for anyone watching this after the event. Thanks for taking the time. All right, so tonight we're going to talk through soil carbon constraints and productivity. So what does that actually mean in the Mallee systems, and how do all these things actually connect? So we're going to do a pretty a bit of a run through a lot of topics tonight. So kind of strap in and we'll see how we go. But there's a lot of things that all connect together. So things like soil constraints, the carbon cycle, emissions, the role of soil testing and nutrition, they're all very much integrated in terms of how we can support our soils well, which in turn gives us the best opportunity to manage our soil carbon levels and support sustainable farming systems. So first of all, we talk about sustainable farming systems. So what does that actually mean? If we think about a native system, they are inherently sustainable because everything is cycling in place. So when things die, they then get decomposed in that place, in that landscape. So there's no loss at all. So as they are inherently sustainable because they are self-sustaining, because of the fact that they're in situ. If we look at our agricultural systems, in direct contrast, we've got things coming into the system, but just as importantly, we've got things going out of the system. So we've got our inputs and our exports going through. So in comparison to our native systems where all our plant material is recycled at the point of growth, in our agricultural systems, we rely on product removal. So that means that we need to have a mass balance of our inputs and our outputs in these systems in order to be sustainable. When we talk about sustainability, the next thing we tend to talk about is soil health. This is something that is only very recently started to become defined as such. It's been around for a long time, and it's been the term itself, I think, was coined about 20 years ago, but it's always been quite hard to quantify what a healthy soil looks like. If we take it right back to the start with our soils, we really think of there's three components in our systems. There's our physical condition, so having a good physical structure, infiltration, ability to move oxygen and roots and biology through the system is our first part. Having adequate chemical conditions is our next part of the puzzle to ensure that our system can function, because the chemical parameters are what we call in spec for what we're looking for. The third part is our biology. So if we were to say, well, what does this look like? We would say that we want a diverse microbial community. How these three things sit is really looking at first our physical condition to ensure that water and nutrients and oxygen can actually move the way they need to do, and that our plants can put roots down and emerge through those systems, and that the chemical conditions support that. These set the house, or the framework of the soils within which the microbes can function. So rather than saying, I want a healthy soil, so I'm going to add microbes or focus on the microbes in the system, in reality, we need to set up the house so that the microbes can do their job. Recently, I had a good conversation with a soil biologist called Dr Cassandra from CSIRO, who spent his whole career working in soil biology and agricultural systems. Key message that he had, which I thought was really resonated, is that all soils have all the microbes they need. When they do all the soil biology measurements, everything is there. If they're not functioning, or if they're not seen to be working, it's because there's something limiting the ability for those microbes to do their job, either a physical limiter or a chemical limiter in that system. So I thought that was a really nice way to focus on it, that everything's there, we just need to set up the house for them. The other thing we talk about is what's a good soil or what's a bad soil. There is no such thing as a good soil or a bad soil. It's really every soil was evolved in a different part of the landscape through different processes, and so they're just all different. So the key part of what we can do in these systems is actually to manage the soil you have. The first part of that is actually to know what soil you have. So understanding what's happening below the surface and just knowing what you're dealing with is actually the first part of building a sustainable farming system. If we don't know what we've got, we can't manage it, and we can't prioritise our investment into our soil amelioration activities. So let's talk wine barrels. There's a very famous kind of theory called the law of the minimum, or Levy's law of the minimum, which talks about how a barrel can only fill to the level of the lowest hole, or the lowest broken wood beam. So whatever is causing that hole in the system is then the full limiter for the whole system. And this was derived specifically for agronomy and for our agricultural systems. So rather than just throwing in what we always do into our soils, the first part is understanding what's the handbrake in the system to ensure we actually address that first. When we're looking at these key soil properties or constraints to consider when we're looking at our wine barrels, there could be a range of factors, which is why understanding our soils and measuring what we've got is really important. The first set of constraints or properties are our physical properties in the system. What is our soil texture? So our clay content, our cation exchange capacity, which is part of that, our ability to hold and move water in the system, our soil structure, which then supports our infiltration and plant growth. If our soil is compacted or it's pugged under extraordinarily wet conditions, if we get waterlogging because we have impermeable layers in the system, if we're dealing with sodicity or dispersion in our soils, if we've got slaking soils, which mean that we can't physically break those soils open to ameliorate things like compaction because they will just collapse all themselves. What's our key physical limiter? In terms of our chemistry, again, we're talking about cation exchange capacity, which is driven by our clay content and our texture. So if we've got more cation exchange capacity, we've got greater chemical buffer in the system, which is a good thing in terms of resisting chemical change. But if things go off the rails a bit, it takes more effort to bring them back on. Whereas in our sandy soils, which are common in a lot of the Mallee, our low CEC and our high sand content means that things can change quite rapidly in our systems, but we don't need to put a lot of inputs back in to bring them back to speed. pH and acidity is a massive issue across the whole agricultural landscape, and it's something that is becoming more and more of an issue within our Mallee systems. Salinity is something that we always need to keep in mind. In the past, we had a really good handle on dryland salinity and the role of plants, deep rooted plants in the landscape in managing those systems. As we've got much better at our summer weed control, we don't have the deep tap-rooted summer weeds in our systems as much. So there's pockets of dryland salinity coming back through. So understanding what's driving those processes and what we can do about them. Again, sodicity and dispersion from a chemical perspective, something to consider. And then our fertility and our nutrient availability piece. So fertility being a driving part, not just nitrogen, but the other nutrients as well. Do we have enough nutrients in the system? Do we have toxicity of things like boron in our high pH systems? Or as we go into our acidic environments, if we have aluminium toxicity, if we've got boron deficiency in some of our systems, what's happening with our potassium, what's happening with our copper and zinc. So understanding the conditions in our system is a really good way to start. Now, let's think about this in terms of our carbon cycle. And coming back to how does setting up our soils to do well then flow through to what our organic matter and our carbon actually looks like. So first of all, understanding what our constraints are is a key part of then growing the best plant that we can. Growing the best plant that we can links into our carbon story because the key way to capture carbon dioxide from the atmosphere into the soil is through photosynthesis through our growing the best plants. So if we have more plants in the system, we have more ability to bring in that photosynthesis to capture that carbon dioxide. We then grow our biomass, and it's that plant biomass that is then converted into organic matter. So our inputs of carbon into the soil is completely dependent on setting up that plant to do the best job it can. The other part about this diagram that I just wanted to flag with you while it's up is not only is photosynthesis the key way to pull carbon dioxide out of the atmosphere into the soil, the key loss pathway of carbon dioxide back into the atmosphere in our cropping systems is through microbial decomposition. When we talk about that, it's actually microbes decomposing that organic matter. The reason why this is such a big deal in our systems is that if we think about the microbes that we want to have and that are working for us in our soil environments, most of those microbes, like us, breathe in oxygen and they breathe out carbon dioxide. So if we have a lot of microbes in the system, we have a healthy soil, functional microbial community, we're actually pushing back a lot of carbon dioxide into the atmosphere. This is why it's called a carbon cycle. It's not a one-way street into carbon dioxide from the atmosphere into soils. The cycling process means that a lot of it's going to come back out again. So when we look at that, the key message around carbon in our systems is around the amount of biomass coming into the system. So from a farming perspective, that is the key part to think about, and the key thing that you can influence within your systems, productivity gain, and what that means in terms of our soil organic matter. So as I mentioned, those biomass inputs are the key driver of soil carbon in our systems. And we know that because we've got this decomposition process where our plant material, our litter and our residues come into our soils, microbes break them down into smaller and smaller bits. Because microbes are breathing, they're then pushing out carbon dioxide or respiring carbon dioxide back into the atmosphere. And our carbon molecules in the system are getting smaller and smaller as they break down. Now, we all know that there's no beautiful utopia of perfect plants going into the system, lots of biomass, continuing to build this organic matter bank in our soils. If we think about what our kind of hierarchy of limitation in these systems are, the greatest influence is climate. So in our tropical and subtropical environments where we can grow a lot of biomass, we can increase our soil carbon levels to quite high levels because we're continually dumping a lot of organic matter into the system. We're respiring a lot of it, but our net organic matter value at any point in time is quite high. In our low rainfall zones, we grow less biomass. So that inherently means we have less organic matter going back into our soils, and we have less ability to influence that because we're limited by our rainfall. The next limiter is our soil type. So within our rainfall environment, so within the Mallee systems, low rainfall types, if we have a little bit more clay in the system, we can actually hold a little bit more carbon. We know that our sands are very low in charge, have very poor ability to chemically bind and hold on to organic matter compounds. Whereas as we increase our clay content, clays being highly charged have a greater ability to hold on to that organic matter and bind it in a way that it is protected. So our soil type has a massive influence. And by the way, because our soil type also influences our water storage, if we do have a little bit more clay in the system, we are going to hold a little bit more water, we're going to hold a little bit more nutrients. We might grow a little bit more biomass as well. The third lever is our management. So that's around how we can bring biomass into the system and our fertility. So how do we grow a good plant? So we tend to get these mixed up a little bit sometimes in our when we're thinking about what we can do in terms of carbon systems. There is a lot of emphasis on management as a tool to improve our soil carbon levels, but this has to be considered within the context of the climate and then the soil type that you're working. And with anything, all our systems have a threshold. So we're not going to increase our soil carbon levels into the future forever. We're going to result in some flattening out, and we're going to have to do more and more inputs in order to get even the smallest changes as we get close to those threshold levels. Okay, so now that we've gone through all that, let's have a think about what is soil carbon in its basic form. When we look at it, we can see this organic matter, like that's inherently what we think about. We think it's a humic type material, it's humus, it's all these good things. But the key definition for it is decomposing plant material that we can't see the origin of it. It's broken down to the level we can't really pick out our leaves and our roots anymore. They're starting to get broken down into that basic base compounds. So because of that, we know that this material is highly variable. There's a lot of different types of structures in there, root material, leaf material. There's a lot of variation in what's in there. What we also know is that organic matter as such isn't just carbon. Not only is there carbon in there, but there's all the other nutrients as well. And this makes sense because we know that a plant takes up all these nutrients in order to grow a good plant. And then we're actually putting that organic matter back into the system. So we're taking all those nutrients with it. So as we've talked about, the carbon in the system, the organic carbon, is within our organic matter systems. So carbon is just one part of what's going on. The other really exciting thing about carbon in our systems is that it can't exist in organic matter without all the other nutrients. So organic matter as a mass actually has a consistent ratio of nutrients. And if one of those nutrients is limiting, that means our carbon is limiting as well. We talk about the variation in the compounds and the structures in our systems. If we go down to really small levels in our soils, we can actually pick out these really microscopic type parts of organic matter or decomposing material, and we can start to see the types of compounds that are present. And really just showing that even as we go down to incredibly small sizes in our soils, we still have variation in what is happening in our soil carbon types. There's some lab tests that will report organic matter. And what's confusing is you go, well, is it organic matter? Is it organic carbon? Which one should I be looking at? We know, because we know our chemistry, we know our balance of carbon to other nutrients in our organic matter, there's some standard calculations that are done to show that organic carbon, which is measured because it's an element, it can be analysed. We multiply that by 1.72, and that gives us our organic matter levels. So they're just a different way of reporting the same thing. We talked about these ratios of nutrients with carbon in the system. A key ratio that has a big driver in our biology is around our carbon to nitrogen ratio. So a C/N ratio of 10:1 means that there's 10 parts of carbon in our soils to 1 part of nitrogen. And this is a really standard metric and a really standard ratio across our organic matter. So what does this actually mean when we talk about these ratios of nutrients and carbon, and how can we influence what's going on? Some really cool work was done in the early 2000s by a guy called Clive Kirkby out of Surrey. He went around the world and he measured organic matter and he measured the nutrients in organic matter. And his theory was that there was this consistent ratio of nutrients in there, that they would exist in very confidently considered ratios, and that they all kind of made sense and related to each other. So what you call a stoichiometric balance. In his work, he measured Australian soils, which on these graphs are shown by the black dots, and then he measured international soils. And you can see the first bit around our soil carbon to nitrogen levels really comes into that 10:1 story. So if you look at our total soil carbon here, and then our total soil nitrogen, and this is within our organic matter, we can tell that even as our soil carbon levels increased, our nitrogen levels increased. And if we look at these ratios, if we have a 10% soil carbon level, which isn't really that common in our Australian systems, but can be seen internationally, that equates to about a 1% total soil nitrogen level. So very linear relationship. Our soil phosphorus levels show a little bit more variance internationally because of the methods that are used to show our phosphorus and because of the mineralogy involved. But in our Australian soils, which again are these black dots, we can see a very strong relationship between our carbon and our phosphorus. Same with our sulphur levels. As we're increasing sulphur in the soil, we're increasing our carbon levels. The key story with all this is that fertility and carbon are completely interconnected. If we support the soil fertility to grow good biomass, that biomass then coming back into the system is then contributing carbon and nutrients in there. If our soils are low in one of these nutrients, that will then constrain our soil carbon levels to that same level. So it goes both ways. We talk about carbon levels and soil carbon values as if they're a static, non-negotiable black box that's not going to move. But in fact, our soil organic matter in our system is in this continual state of flux. And we talked about it in terms of the continual microbial breakdown of that material. So rather than thinking of it as this black box, we really need to think about organic matter as this completely cycling approach. And we know that because we're putting our biomass in, it's getting broken down, and then we're losing it as carbon dioxide. And we're continuing to put organic matter into the system. The other thing to consider is that the benefits that we get from organic matter in terms of our soil structure, our fertility, our ability to hold water and nutrients, our microbial activity, all those things that are really good for us, they all occur through that decomposition process. So if our soils weren't breaking down, we wouldn't be getting these values. So it really shows that it's that continual cycling approach which needs to be recognised as a key part of that system. And as I mentioned before, we've got our oxygen coming in and we've got our carbon dioxide coming out. Now, there's something just wanted to come back to in terms of this carbon to nitrogen ratio and what it means in terms of our ability to hold carbon. A key question that a lot of farmers ask is they're doing everything right, they're retaining their stubbles, they're doing everything great, but their soil carbon values aren't increasing. So I just wanted to work through that process, which might help explain why you're not seeing the results that you thought you would. So if we think about within our organic matter, we have our carbon and we have our nitrogen. And our organic nitrogen, which is present in decomposing plant material in our organic matter, is carbon to nitrogen bonded. So we've got carbon by nitrogen molecules in there. So it's very simplistic, but it's kind of how it goes. Now, going from these complex carbon nitrogen compounds into what we call nitrogen mineralization processes. So the breaking down of organic matter to release nitrogen for plant growth, we talk about that as our nitrogen mineralization to create what we call mineral N. Now, when microbes break the carbon-nitrogen bonds, there's a series of microbial enzymes involved in this pathway. The first thing that happens is they create ammonia through that process. That's then quickly converted to ammonium, which is NH4, which is a key nitrogen measure that's on most of our soil tests. The next pathway from that is to nitrite, which is NO2, and then from there to nitrate, which is NO3. So first of all, this process of nitrogen mineralization is providing that nitrogen flush for our plant growth. We measure this on our soil tests through our mineral N, which is our ammonium and our nitrate levels. Now, this microbial process, which breaks the carbon bonds, results in the loss of carbon as our carbon dioxide, right? So we're breaking those bonds, microbial respiration kicks in, and we get a lot of loss. Now, let's say we're mineralizing, I know, 10 kilos of N per year, or even let's say 100 kilos of N, just to keep the maths really simple. We've got a carbon to nitrogen ratio of 10 to 1. If we're mineralizing 100 kilos of nitrogen per year, per hectare, that is then taken up by plants and grown and harvested. By this 10 to 1 ratio of carbon to nitrogen, That then means that there's a potential loss of up to 1,000 kilos or a tonne of carbon as carbon dioxide through that process. Now, if this process was happening all the time and we weren't replacing carbon and nitrogen into the system, our soil carbon levels would deplete over time, which we saw happen in a lot of our traditional cropping systems where we cultivated them all the time. We continued to expose new organic matter for decomposition. We continued to decline those numbers. Now, if our soil carbon values are consistent over time and we're continuing to pull off a heap of material in harvested product, right, and we're maintaining our soil carbon levels, that actually means that we are replacing what we're taking out of the system. So in effect, maintaining our soil carbon values is the definition of sustainable farming. So if this is the effort that it requires to just maintain soil carbon, imagine how so much more is required if we were to increase our soil carbon levels, particularly in our low rainfall zones in the Mallee. We've got limited biomass coming in and we've got limited opportunity for nutrition. So if we're maintaining, that's already a really, really good thing. So the key message from that is really to manage our expectations. So even just maintaining carbon takes resources, takes inputs. Knowing that each system has a threshold of carbon numbers, with our clay having more ability than our sands, we're rainfall dependent, we know that there's only so much we can do. And the closer we get to those thresholds, the less carbon increase we can have per our unit input. And knowing all our inputs in some way costs money. The other thing is, if we want to change our management to increase our soil carbon values and sort of tick up that threshold into a higher value, that change needs to be maintained. So if we're getting close to our thresholds, we do something new or additional, we get to a higher level, and then we stop doing whatever it was that we're doing, our values will start to come down again. So this means that if we're adding organic amendments in some way, compost, manures, biochars, whatever it is that we're saying that we're doing and we're going to increase our soil carbon values, we need to continue doing them. Because if we don't, our soil carbon numbers will decline back to our pre-application thresholds. So key factors in maintaining or building our soil carbon in the system. So first of all, we know now that soil carbon and our organic matter is a product of the system. Carbon isn't a driver. It's what happens when we get everything else sorted. So the best way to build carbon is to support our plant growth, grow the best plant we can. By doing this and supporting our plants, we're then also supporting our microbes. This means we need to identify our constraints, right? Like we talked about right at the start, both our physical and our chemical. We need to address our nutrient deficiencies. And a key deficiency that we're likely to see in our Mallee systems is either phosphorus deficiency or potassium, probably our two big ones, with sulfur deficiency also starting to come into play if we don't have a pasture phase in the system that's using single superphosphate. So make sure we've just got the basics sorted in terms of our nutrients. Maintaining legumes in the system is the best way that we can ever maintain and improve our soil carbon levels. All the long-term field research throughout the country has shown that the best soil carbon values, and I'm pretty confident that the best profitability of the systems as well, are those that have a legume in the system. Because of their contribution into that organic nitrogen pool, which then supports that increased soil carbon pool because of that carbon to nitrogen relationship. So this really means that we've got this triple win. So you don't need to worry about focusing on building soil carbon. You just need to focus on what's good for plant growth, which is then good for microbial function, which is good for growing lots of biomass, and is good for our soil carbon levels. So just to put a bit of local context back into this as well, knowing that these are the things that we need to think about when we're looking at all that, saying, well, what would be a first issue or a first look at some of our Mallee systems. So just to give an example of what could be a key limiter is we've got, you know, some of our Mallee sands, and this was around Murrayville, so right on the west, on a sloping dune, kind of, it all looks pretty standard. When we dug a saw pit into these sands, what we found was that our roots were completely dependent on that top 10 centimetres for survival. This is why the system was always quite early to shut off if we didn't get any spring rains, and never had a lot of vigour in there. Now, the first question is, why are the roots only at 10 centimetres? And when we actually explored down the profile, we noticed that this was a complete sand. It was completely compacted, no structure at all, which we expect with our sands. So there was a high bulk density and a lot of compaction in the system, and it was highly acid. So if we've got a highly acid compacted system, the roots are not going to want to go down there. So understanding what we could do to support a change in that is how we can then work through how we grow better plants. And so for this system, considering things like putting a root through, because there's no soil structure there to destroy, adding lime into the system before we did any ripping or cultivation to ensure we could actually support that those first 10 to 20 centimetres really well. But just by physically breaking that up is going to have a massive impact on what we can do with that. But before we did this work, this farmer had no idea that their roots were constrained. So the first message from all this is to, if you're looking to do something around supporting increased plant growth, dig a pit, have a look to see what your roots are doing. You're probably not going to see something as drastic as this, but it will give you some insights into where your first move might be. So from this, I really hope you take a real productivity focus. So identifying what your constraints and your deficiencies look like. So in order to support optimal plant growth and diversity, and with your legumes and your cereals and your brassicas in the system, which then supports your high nutrient use efficiency, biomass, productivity. Hopefully that means that you're using your inputs a bit more effectively for your profitability, which then means that you've got the greatest potential to maintain or increase your soil carbon levels. That in itself would be amazing. But the next win that you get from all this is actually a reduced greenhouse gas footprint. And this is something that's becoming more and more topical in farming, and there's a lot more farmers looking to understand what this looks like. And this in particular is something that we'll be talking a bit more through next week when we're having our workshop. If we're doing everything else well, that's the best opportunity to be really efficient in our systems, which inherently drives a low emission farming system. Emissions are due to losses. So if we're doing everything well, we've got less losses in the system. So let's have a look at this. There's also a lot of concerns and queries around what emissions look like in sort of carbon sequestration and what that means in terms of carbon stocks and credits. So we'll have a bit of a quick spin through those before we finish. So if we think about this whole carbon stock story, the key part of anything around measuring soil carbon for increased soil carbon stocks and potentially credits is the requirement to have a baseline. So that's when there's initial high intensity sampling done to know what carbon you've got in the system to start with. So if the challenge with this is if you are already doing good things and you're towards the top of your threshold of soil carbon in your climate and your soil type and your system, you do have limited ability to move. And in the Mallee systems, those thresholds are really quite low. So there's only so much we can do to improve. But theoretically, let's say you wanted to have a crack at this. So this would be your baseline. And then in time, you might increase your soil carbon level. So you look at that green box and you go, well, that's my increased soil carbon, that's my stock, that's something that I could potentially trade or monetize. When we pull that apart, we know that the emissions required or produced in growing that carbon, which means growing the plants, and potentially emissions from the animals, if you've got livestock in the system, to create that carbon then needs to be discounted from that. So if we look at that whole box expanded, and then we say, well, actually quite a lot of that box gets discounted, either through method discounting, because it's a soil carbon number, which in itself is highly variable, and because it's going to have produced a lot of emissions since the baselining. So even if you've grown carbon in your system, you've only potentially grown a small amount, which you can then do something with. In terms of our emissions and stuff in our systems and, potentially requirements or considerations around reporting of that, livestock is far and away the biggest single emission bucket in farming. And that's because of the enteric or rumen-based fermentation, which creates a lot of enteric methane. In our cropping systems, nitrogen fertilizer manufacture and usage is a key part of that, particularly because the harbour wash process, which creates ammonia, is really energy intensive and creates a lot of emissions in the production of that urea. So then those embedded emissions then come on farm and be reported as part of the farm-based emissions. In terms of things that we can do to reduce our emissions on farm and the role of nitrogen fertilizer in that respect, there's our inhibitors and our polymer coatings. There's a few products out there. So green urea, which is a urease inhibitor product. Entech, you might have heard of. Sustain is a CSPP product with the inhibitors and stuff in it. None of these are silver bullets, and there's a fair chance that they may not be appropriate in your systems. But if you were interested to learn more and go, actually, yeah, there might be a fit, want to have a bit of a play, then yeah, that's a good way to start. The other key part of or driver of our on-farm emissions is our stubble and ground cover management. So that's really plus or minus burning. If you're burning, your emissions go higher because of the nitrous oxide and methane loss when you do that. If you're retaining your stubble in any form, then you've got some biological emissions because of that breakdown process, but they're not as high as what you have when you burn. All right, so just to finish up, just wanted to talk through some of the research that we know in this space. Thinking about low rainfall farming systems, there was an experiment done a number of years ago, which you can sort of tell how the story ends because of the title. But this was based up around Condobolin, so low rainfall zone in New South Wales, where a number of different farming systems were measured. Conventional tillage, mixed farming, reduced tillage, continuous cropping, and perennial pasture. Now, the key piece from this is that the short-term outcome may not represent long-term persistence. So it seems like a bit like a banking ad. So the key thing to look at is this biomass fluctuation over time, and then our inputs, how those fluctuate over time. And I just wanted to show this to demonstrate that if we've got our total organic carbon levels in 0 to 10 over years, and then our 10 to 30 carbon levels over these years, all of the systems increased in carbon over that time, and then they all decreased. The only one that decreased less, so came back on par with starting levels, was our perennial pasture system. Everything else ended up lower than what it started with. And this was true in the surface soil and in our subsurface soil. So this is something to consider if you're thinking about carbon credit units, particularly as it relates to soil. So if you think about our credits, these are financial mechanisms for the Australian government and other organisations to pay landholders for capturing storage. This additionality clause is really important. So new carbon and new practice. So let's say in this previous work, you started in a conventional cultivation story, which is the black circle, and then you converted that into a perennial pasture, which was the best system, over the time things increased, they still came down again. So yeah, the pasture didn't come down as much, but the commitment to additionality and retaining that carbon over time could not be supported. So things to think about when talking about ACCUs: risk of reversal, there's legal considerations and financial considerations to consider. And there's a few websites that you can have a look at to see more about the schemes and how they work. Just finally, wanted to just flag some really recent research that was done, which really highlights this challenge around biomass fluctuations over time and what that means in terms of soil carbon credits. So this was a recent publication with a whole list of authors, and I've listed the authors because these researchers are the researchers working in the space across Australia. So these are the ones doing the independent science-based research. And I've put them all in there just so that you can see who they are. What they did was actually look at these carbon projects that had been issued with credits. So these are 4 ERF, Emission Reduction Fund, carbon credit projects that had carbon credits issued. So they looked at these sites that had that, because all this is publicly available, and they mapped out the historical biomass over these systems over time. And they did that through measuring something called the NDVI, the Normalised Difference Vegetation Index, which is a biomass indicator. Now, what they show is if we're looking at from 2000 onwards, the biomass fluctuates a lot. And the fluctuation is generally due to rainfall and biomass growth. So if we look at 2020, which is ironically when some of these projects started, we just come out of 2 years of drought. So there's very little biomass in the system, low soil condition. Then when the projects were registered, so they were baseline then, and then 5 years later they were measured again. We've had some good seasons and our biomass increased and our carbon levels increased. Now, what you can see here is, so that the really noisy lines are the actual numbers, and then the smooth lines are basically the time series averaging that they've done. The green is what was done on those project sites in terms of measurement. The grey is what was done next to them. So they're using that as a control. So basically to say, if they hadn't set up a project and done something additional, what would have actually happened? So we can see for all these, the dotted line of implementation, the biomass was lower, carbon was lower. When it was remeasured, biomass was higher, carbon was higher. The key message in this paper is that there's the climate connection through to soil carbon is very strong, which makes it really hard to pull out the impact of management beyond climate. So from this, we can see that whilst paddock management is important and doing the right things in field is really important, that provides the nuancing or the finer refinements of what happens with our soil carbon over time within our broader seasonal conditions. So finally, just to flag the importance of good soil sampling and measurement. So if you don't have numbers, you can't manage and you can't prioritise your investment. So good quality soil sampling and testing is a really good idea in terms of understanding what your key limitations are, how to optimise your soil condition, and then what your key decision points and costs looks like to do that. We tend to not care as much about our soil sampling, and people get down in paddock, it's all done in a bit of a rush and may not be given the care it needs. If we think about the decisions made from those soil tests, it makes sense that those soil samples should be treated with the best possible care to give the best quality data at the end. Things like how our site selection is done. So GPS locating within our soil types. So no big transects. Our soil sample collection, making sure we're dealing with multiple depths to understand where our key limiters might look like. Ensuring our soil sample handling and process is appropriate. Cool storage, express post to the lab, use good quality labs, and ensuring that the soil analysis that's done is appropriate to what you need. Got some general comments there around testing, but the key part is really flagging that if you're going to do the work, make sure that you use best protocol to do it. Using your NATA accredited labs, using the same labs and the same tests at the same time of year, and ensuring that you're using standard methods of sampling. So shovels are not great, not likely to give you a consistent result. Just some final comments to flag how if we're looking at soil carbon values across the landscape, for example, which is what these numbers are, if we ran the transect through, we would get an average soil carbon number. We would never see a change in that over time because of that high level of noise in the background. Whereas if we selected discrete points in that landscape, measured those and came back to those over time, we're highly likely to see impact of our management because we're taking out a lot of that background noise. The last thing I just wanted to flag is that we tend to think that we're in our own little world in Australia, and even in the Mallee systems, that we're just working in that environment. The world is very small these days, and a lot of the buyers of your products in grain coming from an international perspective. So being able to articulate the good practices that we're currently doing is a really nice first step in telling that sustainability story with what we're doing. So don't discount the things that you've always done, which are just assumed to be good practice, retaining stubbles, direct drilling, crop rotations, that kind of thing. Those basic things that we consider as standard, it's just how we farm, they're still considered quite novel on the international context. So just want to take a moment to actually say, look, you're already doing really well, which is why it seems like there may not be the opportunities and benefits that we might expect because we can't hit that additionality and those change metrics that some of the world is looking for. But that's because we're already doing lots of things really well. So just kind of consider that and recognise how good your systems already are, but then look for the refinements in those systems, knowing that we've already done a lot of the heavy lifting. So finally, just wanted to come back to flag that we know our soil carbon is present within our organic matter, which is continually fluxing in our systems. And it's the decomposition that gives us a lot of the benefits that we're looking for. Increasing and storing soil carbon is never guaranteed, as much as we'd like to think so. And you shouldn't have to choose between growing a food or fibre and growing soil carbon. If you focus on agronomy, efficient use, input use, manage your soil constraints, doing all the basic stuff really well, that's your best environment for growing soil carbon. And soil testing is the best way to understand and manage what you're doing and seeing the impact of your practice over time. And that's all. So I apologise for that was a lot of information in there, but I couldn't decide what not to share with you because I think it's all really important. So hopefully you can pick up something from that and see how you go. Thank you, Jack.
Thanks, Cassie. And yeah, no, I definitely agree. It's all very important information, even if people aren't looking to, enter the carbon markets. And yeah, it really seems that increasing soil carbon and running a low emission system is really a byproduct of just good practice on farm. So we've got just a few more minutes, so we'll wrap things up, but I do have a couple of questions. So you probably touched on a bit of it during the session. One of the questions was when we're talking about building soil carbon, what's actually realistic for growers to expect, or even just maintaining it, as you said, is an achievement sometimes. So in terms of gains or changes and timeframes, like would you be looking over decades to track changes in soil carbon?
Look, I think within 5 years you'll get a sniff of what changes might be happening. The challenge we have is because our biomass inputs can fluctuate so much within a 5-year period. You know, because if we hit a drought, things will go down. A good year, things will go up. So looking at those numbers as more of a longer term thing, it is hard. But I think that maintaining soil carbon level is actually the gold that we really need to be looking at. If it's not going down, is actually amazing. A lot of the recent research and modelling that's coming out of some of the farming system trials around the country is showing that most of those are going down. They're just going down at different rates. So if we can maintain, that's actually fabulous to do. So I know I already said it like heaps of times already, but that's amazing. In terms of any increases, so if we've changed, so we shouldn't even be expecting to see a change in that number unless we've actually made a change in our system. So if we've gone from a wheat canola system to a wheat canola legume or pulse, for example, we might start to see a change in that within the first set of that rotation, you know, between 5 or 6 years. If we wanted to really be confident in that change, then we're probably looking at 10. So that's the challenge. But the other part of that, which makes it's really hard to measure, is that we measure soil carbon, but in fact there's different pools of carbon that do the job. The pool of carbon that does the job around supporting nutrient cycling, microbial function, water infiltration, and holding capacity, ability to hold nutrients and support increased moisture within that seeding environment. That's all part of what we call our particulate carbon pool, which is our fast cycling pool. So even if that pool is highly functional, it may not increase as much. Whereas the pool of carbon that's responsible for our decadal increases is what we call our recalcitrant pools or our humus pools, which are kind of very fine chemically bound carbon that isn't going to move so much. Those pools are really small and they only move really slowly, but we're not going to pick up differences in those within the first 10 years. So look, if we can get an increase in carbon, like even a 0.1, so change from 0.5 to 0.6 or a 0.7 to 8 or something, that's phenomenal. That actually equates to quite a lot of tonnage increase in terms of our carbon in the system. So, you know, sure, I could say, yeah, we can do all these things, but I'm sure you can do them and then they'll come back again. So if it's, yeah, do the things for the productivity and the system benefits. And if you get an increase in soil carbon, then that's amazing. And I didn't really answer your question.
No, that's good. It's a difficult question. Yeah, particularly when maintenance is an achievement in itself. So the other question I had for you is really for those that might want to come along to the workshop next week. Are there any particular soil tests that they should bring along to that session? Might be worth discussing or looking at.
Yes, pretty much anything they've got. Ideally,
depending on what challenges they're facing. So
yes, yeah, but so most of the soil tests that farmers will have will be those 0 to 10 numbers, which is more about comprehensive tests that kind of show a bit of everything. The challenge with those, I find, is that they show everything, but at the same time, they're actually quite hard to interpret. A lot of farmers challenge around, okay, so I've got the numbers now, what do I do with them? So a key thing I'd like to go through in the workshop next week is actually going through some standard tests from some of the different labs that you might be using, and actually work through what the numbers actually mean so that you can then use them to make decisions and be informed in tracking them over time and what that actually looks like. So we'll talk a lot about nutrient supply, what good looks like, what some red flags in the system, and particularly what some of our constraints in the soils look like. So that would be a starting point, is the 0 to 10 numbers. If anyone's got subsurface numbers, so 10 to 20, 20 to 30, for example, bring them along as well, because we can certainly work through those. The only other type of soil test that might have is your deep nitrogen testing. If for those who are doing it, whether you're sinking deeper cores purely to look at your nitrogen and sulfur system. Feel free to bring those along if you like. We will still talk through what they mean. But being informed of those numbers does require more system information to know what your nitrogen budgets actually should look like. So bring them along. We can have a starting point discussion about them. And the other thing is, whilst the focus of this workshop is for farmers to understand what's happening, I would certainly be quite happy to any agronomists who want to come as well, Jack.
Yeah, absolutely.
To ensure that everyone is part of the system actually understands what's going on. So there's, any agronomists around or for the farmers who are keen to come, bring your agro along as well. And we can make sure that the information that we work through is really valuable for you.
No, that's perfect. All are welcome at the workshop. So I've got a QR code on the screen if anyone would like to scan that and register for that session. It only runs for a few hours, but 2 p.m. till 5 p.m. Monday afternoon, and it is catered. So hopefully we'll see a few people there. There's also another QR code on the screen if anyone would like some more information, either before the session or at any point in future. You can scan that and fill in your details there, or you can contact me directly if you'd like. But we're actually out of time, so I think we should wrap things up. Thanks everyone for your time, whether you're viewing live or in future. And thanks, Cass, for your great presentation.
Thank you, Jack. We'll see you next week.